Okay, hi everyone. Welcome to this video where we do a review of how to draw free body diagrams. This is 3.2, the beginning of the net force lesson, and you'll remember we did this just before March break, but I'm sure a lot of you forgot. So let's get started. The first free body diagram, I have an iPhone at rest on a table. So all free body diagrams, we start with a circle like this. I'm just going to make that a little bit bigger and choose the right brush here. Okay, so we start with a dot always to represent the object. Now, there's always the force of gravity acting on our object, so that would be Fg. Excuse me for my technology here, just trying to figure something out for today. And you always should be drawing the, labeling the vector with appropriate name and the arrow. So that's the force of gravity. Now, there's also a force of the table acting on the iPhone, pushing it upward. So that would be the normal force. And that's always in the opposite direction, or perpendicular rather, to the contact surface. You'll notice that these two forces balance each other off, Fn and Fg. And when forces are balanced, the object tends to not be moving. So that makes sense that the free body diagram would look like this. Okay, let's continue. An angry bird is falling to the ground. Neglect air resistance. So we're drawing the free body diagram for some angry bird that's in the air. So there's my dot to represent the angry bird. Okay, automatically I can add the force of gravity because we know that gravity is acting downward. Now, because I'm using this awkward setup, I'm just going to write Fg, but you guys should be putting the little arrowheads on top of Fg. Okay, what else? So is there a normal force? Well, no, there's no surface that the bird is interacting with. Is anyone pushing the bird? Implied force? Well, no, no one's pushing the bird right now. Is there a rope? No. Is there any friction? Well, no, we're not sliding against anything. And is there any air resistance? Well, no, we said to neglect air resistance. So that is my free body diagram for the bird as it's falling through the air. Now, note that this doesn't necessarily tell you that the bird is going down. It just tells you the force is acting on the bird, and that is the force of gravity is the only one. Look as well as how this free body diagram is unbalanced. This force of gravity is not balanced by anything else, so we know that the bird, and we're going to learn this later, the bird is actually going to accelerate downward. Okay, let's continue with our next free body diagram. An angry bird falling to the ground. This time we're going to consider air resistance. So we're going to start with a dot to represent the bird. I draw my force of gravity down, Fg. Again, there is no applied force, there's no normal force, there's nothing else acting on the bird right now except for air resistance. Air resistance always goes in the direction, fighting the direction of motion. So if the bird is going this way, then air resistance is fighting it. It's going back this way. Air resistance is also a very small force, so I'm going to draw it as a smaller arrow. And you can see the angle is approximate, and that's F air. Again, sorry for this new technology. I'll figure something better out for next time. Okay, let's continue. Now we have an angry bird at its highest point. So you remember when a bird gets launched, it's going to temporarily, for just a split second, not be moving up or down. It's going to stop moving up or down for a split second at the top of this parabola. But that doesn't really impact the free body diagram. I have my dot. Force of gravity is always acting on any object on Earth, right? You can't escape gravity even for a split second. There is nothing else happening to this bird though, no other forces. There might be a little bit of air resistance, and because the bird is still moving horizontally, the air resistance would be acting this way. But again, the air resistance would be very small, and often I'll tell you to ignore it. Okay, let's continue. Oops. Okay, the angry bird as it is being launched. Okay, well, let's start with the dot. Now, before we do anything, I know gravity is impacting my angry bird. That's a given. Now, as it's being launched, you have to imagine right now the bird is being launched forward by this elastic band. So something is pushing on this bird. and it's pushing in this direction. I'm going to make that a little bit longer. We assume it's a big pushing force. And we call this FA, or F applied. That's an applied force. That's if somebody's pushing on something or pulling on something. So in this case, it's this elastic band is pushing on the angry bird. Technically, there's a very small amount of air resistance, something fighting me as I'm moving through the air. This is so negligible. Again, a lot of the time we're going to ignore air. Technically, there's not a normal force here because I'm not at rest on a surface. I mean, this rope is applying a force, but I'm not going to consider it a normal force. We usually reserve normal force when something's sitting or is on some sort of surface. Okay, now we have a hanging ball. There's my ball right there. So I'm going to, oh, just got an email. So there I draw my the dot to represent my ball. Now there's always a force of gravity acting on this ball. And then we see that, is anybody pushing on the ball? No. Is it resting on the surface? No. Is it moving through the air and have air resistance? No. But we can see there are these two strings holding it up. One of them acts like this, and one of them acts like this. This is going to be Ft. Hopefully you remember T is the tension in the rope. And we put a 1 there because that's one of the FTs. My other FT, Ft2, is over here. And again, remember what I said, when the ball is at rest, which it is, we're going to find all these forces add up to 0. They all balance out. That's what we're going to see in lesson 3.3. Okay, next we have this boat from Clash of Clans. It looks like he has a little motor here. Let's call it a motor. So first I start with the dot. Now right away, gravity is impacting this boat. We know that for sure because it's on Earth or some planet. Now, in this case, the boat is not going down, like the force of gravity isn't unbalanced and just pulling it downward. There's something pushing the boat up so it doesn't fall in toward the center of the Earth. That upward force in this case is the upward force provided by water, which is called buoyant force. And you really only see this if you're in the water. This should be a B. Okay. It looks like there's some sort of, well, maybe it's not a motor, maybe it's just the sail. So we're going to have some sort of applied force. Whether you call it a motor, whether it's the force from the sail, there's some applied force. Let's leave it at that. I don't want to get too confused with friction. I don't know if we'd really consider it friction moving through the water. Let's just leave it like that for now. Okay, let's continue down to, oh, my favorite game, Legend of Zelda. Now what I have to do is just make a new file here. Let's save. Okay, so we have Link is pushing a block. So I'm going to draw a free body diagram for the block. So there's my dot. Oh, there's always gravity acting downward on this thing. Now, the block is not accelerating downward. There's something balancing the force of gravity, and that would be the surface that the block is resting on. We call this force the normal force. It always acts perpendicular to the surface. So the surface is here, so the normal force goes up this way. Those two happen to be perfectly balanced. Sometimes when forces are perfectly balanced, we put these little cross lines to show that they're the same length and they balance each other off. Now, Link is pushing really hard. Which way is he pushing the block? He's pushing it from the right, this way, like pushing toward the left. So I'm going to draw Link's applied force like this. Now, if Link had his way, the box would go moving in this direction, but we know it doesn't. It doesn't move. That means something is balancing this applied force in the opposite direction. Something's fighting Link and preventing him from pushing the box. Now think about you, if you were pushing a really heavy filing cabinet, you wouldn't be able to get it to move. That's because the friction between the block and the surface is too strong. So this is a friction force that's opposing Link, and we call it a static friction force because the object isn't moving. These two balance out as well. Remember what I said on the last page. If all the forces balance out, the object tends to not be moving. So there we are. That's my free body diagram for this block. Okay, now we are in cruising USA. I'm going to draw this free body diagram from the side. So even though the car is going forward, let's draw it from the side. First of all, easy, we're going to draw the force of gravity. Now this is balanced by the road that's pushing up on the car, preventing it from falling to the center of the earth. That's my normal force. Now the car is some sort of engine. The engine is pushing the car forward. Think about Fred Flintstone with his feet. He makes the car move forward. Well, now we have engines that do that. Is anything fighting the car going forward? Well, probably a little bit of gravity, or sorry, not gravity, a little bit of friction, Fk. We use Fk for kinetic friction. Because the car is moving, the force of friction is called kinetic friction. There also is probably a very small amount of air resistance in this one. Again, usually we don't need to worry about air resistance. It's so hard to write with this pen. Okay, let's keep going. What do we have here? A few last hard ones. So we have Mario at rest on a hill. Okay, so let's start with Mario. Well, first of all, he's just sitting there and he has gravity acting on him because whatever world he's on, there's still gravity. Now, there's a normal force. Remember, the ground is pushing back on Mario, but it's not pushing straight up. It always pushes perpendicular to the surface. So if the surface is like this, the force of normal force is pushing out this way. So you'll see it's at a slight angle. Oops, let's just get that here. Slight angle like that. Fm. Okay, now he's at rest on the hill, meaning he's not moving. Again, remember what we said, if I add all these up, if he's not moving, they should be balanced. And right now, the up and down might be balanced, but the left and right is not balanced. So I would think he's going to move to the right, or move to the left. And that would make sense, right? Imagine if this was an icy slope. Well, we would expect that Mario would be slipping down. So if it was an icy slope, what's the ground doing to him to stop? Sorry, let's say that again. This is not an icy slope. So what's stopping him from falling down, sliding down this hill? Well, something's pushing him up the hill. It's preventing him from sliding. That force is the force of friction. And again, it's static friction because he's not moving. The force of friction is always parallel the surface, or parallel the contact between Mario's foot and the surface. So it's acting this way. Without that force of friction, it would be like he's on an icy surface and he would just slide down. So friction is a bit of a saving Mario's life here. It's stopping him from sliding. Okay, now we have Mario sliding down the hill. So again, let's start with the easy stuff. I put my dot to represent the Mario. I put the force of gravity here because there's always gravity. Now, there's also a normal force. So remember, the ground is pushing up on Mario, but if this is the angle of the ground, then the force of normal is always perpendicular. So the normal force is somewhere like that. Now, in this case, Mario is sliding down the hill, so he is unbalanced. There's more force pushing him down this way, and you can kind of see that, right? The downward here balances with the upward here, so I'm left with an arrow more or less to the right, and that's what he's doing. He's sliding down. However, there's probably a bit of friction that's fighting his motion. If he's going downward to the bottom right, then there's a little bit of friction fighting his motion, and we call that Fk. Why do we use K? Because he's in motion, so it would be kinetic friction. Okay, I think we did these in class. I'll just draw the free body diagrams because we're all here. Let me just go new, don't save. Okay, I'll just draw the free body diagrams for these three last examples. We have two rock climbers sleeping in a tent. What a cool tent to stay in. So now there's a dot to represent the tent. There's the force of the tent and the rock climbers. There's the force of gravity. Now, if I just had that force, they would be, it's unbalanced, so they would be accelerating toward the ground. Luckily, they have this rope here. Now that rope pulls in the other direction, right? Without the rope, they would fall, so that must mean the rope is pulling them upward. That is my tension force. And you can see the two are perfectly balanced, so they're not moving. Let me get to the Titanic. Now, the Titanic has a force of gravity of 2,600 kilonewtons and has a buoyant force that's up like this. Now, as you know, the Titanic hit an iceberg, so the buoyancy was affected by all this water that entered into the ship's hull. And the buoyant force, which should be balanced with the gravity, is no longer balanced. Gravity overpowers the buoyant force, and so as you'll see in 3.4, this ship is accelerating downward. The gravity is more strong than buoyancy. Sad story. Finally, we have this strongman pulling an airplane. So this one, we have the airplane represented by a dot. Has a big force of gravity. It's a very heavy thing. And then it's resting on a surface, so there would be a normal force pushing it up, and that's going to perfectly balance the gravitational force. Now, the strongman Kevin is pulling the airplane, so you're pulling it forward. So he's applying some sort of force, and he's pulling it. He also has a friend pushing the airplane. Okay, so I'm going to call this FA1. That's him pulling. The friend is pushing, but he's pushing in the same direction. So you have to imagine these two forces are kind of teaming up. They're both doing the same thing. They're both moving the airplane forward or to the right in the case of my drawing. Great. Now there would be a little bit of friction. Now if they're pushing it and pulling it this direction, then there has to be kinetic friction opposing their motion, so it would be going in the opposite direction. And friction is going to be small. Because it's moving, we call it kinetic friction. Technically, there would be a little bit of air resistance, but it's not really mentioned in the question, and it's not really relevant to solving this. So there we have my free body diagram. Again, if you want to analyze this, the up and down directions balance out perfectly, but the left and right do not. There's more forces to the right, so we know that the airplane is going to accelerate forward. Okay, that's it for a review of free body diagrams. Hopefully that was enough to jog your memory about how to do this. If you do have any more questions, please shoot me a message on Google Classroom, and I'll try to figure out a better software to record these cool videos. Good luck, everyone, and I'll talk to you later.